was a really cool, very personal introduction. Speaking of learning C++ on a parent's office mate's computer, anyone who grew up using DOS, if you need to format a floppy disk, the floppy drive is the third most important drive on a computer, right? The most important drive is the hard drive. Then the next most important drive is maybe, I don't know, another, the floppy drive that you don't usually use. And then the third most important is the 3¼ floppy drive. So if you want to reformat a floppy disk on your mother's office mate's computer, that's going to be C:\\, right? No. I got in a little bit of trouble that day. Okay, I'm interested in multi-messenger astronomy, and so what that means is using 2 or more of the fundamental physics of nature at the same time to learn something about an astronomical object. Or put another way, to use 2 different kinds of particles. So for example, if you've seen the news from yesterday, there was a big announcement about one of basically the first ever observation of a single event in, a single very distant event in both electromagnetic waves and neutrinos. So my main interest is observing the same astrophysical object in both gravitational waves and electromagnetism, and hopefully someday also neutrinos. So I have sort of a day job and a night job. My day job is sort of data science, working with the LIGO and Virgo Gravitational Wave Observatories, doing a lot of time series analysis, a lot of Bayesian inference. And my night job is working with a number of different astronomical facilities, mostly optical and ground-based, to look for the signatures of those same gravitational wave sources. I'm going to talk mostly about my day job today. So this guy, Einstein, came up with the theory of general relativity about 100 years ago. It is the sort of modern picture that we use to understand space and time. And in a nutshell, what Einstein's theory of general relativity says is that massive objects cause curvature in the fabric of space-time, and that curvature tells objects where to move. So that there's this interplay between mass and energy density and geometry. A consequence of that is that the theory of general relativity predicts something called gravitational waves. These are ripples in space-time. If you have sort of a coordinate grid that tells you how far apart 2 points in space are, as a gravitational wave passes by, it's going to squeeze space-time in one direction and stretch it in the other direction, and vice versa. Gravitational waves are pretty similar to light in a lot of ways. They travel at the speed of light. They travel in 2 polarizations, but there are some big differences. For one, gravitational waves are a traveling perturbation of the metric of space-time, if you will. And so what's oscillating is not electric and magnetic fields, but a strain, a change in length per unit length. Also, unlike light, gravitational waves are, also like light, gravitational waves are transverse. Unlike light, they're quadrupole, not dipole radiation. Einstein was convinced that we would never be able to detect gravitational waves. In 1916, he wrote, "It is obvious that the amplitude of gravitational radiation has, in all imaginable cases, a practically vanishing value." So he was convinced. So at times he was convinced that gravitational waves were a real physical effect, but he was convinced that they were so weak that we'd never be able to detect them, and they'd be completely irrelevant to our reality. On this slide, I'm showing 2 ill-conceived gravitational wave generators to show you that the idea of a man-made gravitational wave transmitter it just cannot exist. So the first one on the left here, this is a gravitational wave signal generator that's sort of a gag device that sits in the theoretical astrophysics meeting room at Caltech. And so it has this pair of weights that are spinning on a little pedestal. And if you calculate the amount of strain that this produces, it's something like 10 to the minus 50. So a fractional change in length of a part in 10 to the 50. On the right-hand side here, this is sort of the opposite end of making a very large, very high, very high velocity device. And so this is actually a centrifuge at NASA Goddard Space Flight Center. This was not set up like this to produce gravitational waves. This was done to sort of test the rollover stability of these SUVs. But if you calculate the emission, the amount of gravitational waves that it would produce, it's something like 10 to the minus 46. However, nature can do much better. The best source of gravitational waves is sort of is again basically a centrifuge. So you take two masses orbiting each other, and they need to be moving pretty close to the speed of light, and they have to be pretty massive. And so the best sources of gravitational waves that you can conceive of in nature are binary star systems composed of two compact objects, such as two neutron stars, or in this case, two black holes. And if you calculate how strong these gravitational waves would be for a source that's sort of in the in a not too distant galaxy, and how strong the gravitational waves would be at Earth, you get a strain of 10 to the minus 21. Now, we've actually known that gravitational waves are real for several decades. And the strongest evidence that we had for a long time came from binary pulsars. And so this is the Hulse-Taylor binary, which consists of two neutron stars, and we see the radio pulses from both neutron stars as those beams pass through our line of sight, and because those radio pulses come at a very, very regular frequency, which is we can use them as very, very precise clocks to measure the orbit of the binary. And so we can tell that this binary that's orbiting with a period of about 7.75 hours is losing 76.5 microseconds per year. And it's losing it at a rate that is exactly predicted due to the loss of energy and angular momentum to gravitational waves. And Hulse and Taylor won the Nobel Prize in 1993 for demonstrating this. Now, with LIGO, we want to detect those gravitational waves directly. And so the way we do that is with laser interferometry. I'm going to back this up because I wasn't talking fast enough while the animation was playing. Sorry. So this is a Michelson interferometer. So you have a laser You have a laser that shines onto a beam splitter and reflects off of two mirrors in two different directions, then recombine at the beam splitter and come out at a detector, which is this white plate. Now, depending on the difference in the length of the arms, you either get perfect constructive interference, and so you see light at the output at the detector, or you get perfect destructive interference and you see no light. And so you can use laser interferometry to very, very precisely measure differences in length to precision that is much, much smaller than the wavelength of light that you are using. So because these gravitational waves are so extremely weak, we have to do lots of crazy things to make them detectable. And the first crazy thing that we do is that we make our detectors enormous. So this is LIGO Livingston Observatory in Livingston, Louisiana. In the bottom of the picture, you see the vertex station, as we call it, which houses the high-power laser, the beam splitter, the readout optics, and 4 kilometers off in either direction are the end stations with those end mirrors. Because these detectors are also extremely sensitive, they pick up ground vibration from both seismicity and also anthropogenic, ground motion, and they're sensitive to all kinds of environmental effects, we have to put them in god-awful places. So, for example, this detector is in a logging reservation in Louisiana. We actually have huge problems with alligators here. And this one, which is actually the one I think is even, of the two that I visited, this is my favorite, LIGO Hanford Observatory in Washington State. This is on the Hanford Nuclear Reservation where we manufactured a lot of the material for nuclear weapons during World War II, and we did it in a hurry, and so we weren't very clean about it. So it's this amazing, desolate nuclear wasteland. And, you know, sometimes we'll actually see blips in our data because of like demolition that's going on the nuclear site to like clean up after these sort of mad science experiments that we did during the Manhattan Project. And we'll have to go out and bale tumbleweed off of these beam tubes to keep them clear. But we now have this global network of gravitational wave observatories. So LIGO stands for Laser Interferometer Gravitational Wave Observatory. As I said, we're going to try to sense fractional changes in length of a part in 10 to the 21. With our 4-kilometer arm length, that's equivalent to measuring a change in length of 2 times 10 to the minus 16 centimeters, which is about a 1/500th of the radius of a proton. In proportional terms, it's like measuring the distance from here to the nearest star to an accuracy of the breadth of a human hair. And we have to play all sorts of crazy techniques on top of making these detectors enormous to make that work. So these mirrors at the end, so in this photograph in the top right is a picture of one of the end mirrors, have to be 40-kilogram chunks of glass that are suspended from pendula that are made of glass threads. And then that pendulum is hung from another pendulum and another pendulum, and all of these these pendulums are also actively controlled to further damp ground motion. We have to dump huge amounts of laser power into the system because one of our noise sources is just sort of photon counting noise. And so we take a 20-watt laser and we put it into, these arms are actually resonant cavities, and so the light makes hundreds of round trips in here before coming out, so we boost this up to hundreds of kilowatts stored in the arms. With all the power that's being dumped on these mirrors, they deform thermally, and so to keep them in just the right shape, we have to actually heat them from behind with a completely different laser system to cancel that thermal deformation out. And the end result is that we actually have some sensitivity to gravitational waves. So this is the signal, the first signal that we've ever recorded from a binary black hole merger on September 14th, 2015. I'm going to play it for you. You're going to see a spectrogram. So on the horizontal axis is time, on the vertical axis is frequency, and you're going to hear the signal after we've whitened the data and bandpassed it to sort of make the astrophysical part of the signal more obvious. So you hear that knock. Now we're going to boost it in frequency, and so you hear a chirp. So that chirp is the signal of a binary black hole merger. And so what's happening is you have these two black holes that are orbiting each other, and as they get closer and closer, they emit gravitational waves more and more strongly, and this is a runaway effect, and so the amplitude and frequency of the gravitational wave signal goes up and up and up until merger, which happens in, it's going to slow down here for a moment. So these black holes will finally merge, form a single black hole, which will then, come on, ring down and settle down into a nice spherically symmetric remnant black hole. So since then, we've detected many more black holes, and so we've assembled sort of a rogues gallery of binary black hole mergers that we've detected through gravitational waves. These purple ones in the lower left corner, these are black holes that we've detected using more conventional means. So using X-ray telescopes to look at a black hole that's accreting matter from a donor star. And we can look at the X-ray emission from that accretion, and we can use that to determine the mass of the compact object. And so all of these black holes have masses of maybe 5 to 10 solar masses. The black holes that we're detecting with LIGO go up to much, much higher masses. The heaviest one so far was the first one, so it was a merger of a 29 solar mass and a 36 solar mass black hole, I believe. And the remnant, or the final remnant, was something like 62 solar masses. So started out with the 2 heaviest stellar mass black holes ever observed, and we made an even heavier one. But black holes are cool, but I think what's much more interesting is neutron star mergers, because when you put matter into the system, then you can get light. So here you have 2 neutron stars that are orbiting in a binary, and up until they get pretty close, physically it looks a lot like a binary black hole merger. But when they get close, the 2 neutron stars start to pull each other apart due to their tidal forces, and they form a short-lived sort of accretion disk. And that accretion flow is going to be the central engine that powers a range of different types of electromagnetic emission. So the coolest consequence of this is nucleosynthesis. So the way this works is we take 2 really dense neutron-rich objects and we pull them apart, so we have a lot of hot neutron-rich matter, and we're going to synthesize a lot of heavy elements in the process. And then those heavy elements are going to decay, and they'll act as a radioactive heat source that's going to produce a signature that we call a kilonova. The dominant nuclear physics process that's going on here is called the R process, or the rapid neutron capture process. And it's called it's called rapid because you're capturing neutrons onto seed nuclei faster than those neutrons can beta decay. This chart here it's sort of like the periodic table, but it's a chart of the nuclei. So on the horizontal axis, you have the number of neutrons, and the vertical axis, you have the number of protons. Along the diagonal, or close to the diagonal here, is what's called the sort of the valley of stability. So these are the stable nuclei. And in a neutron star merger, or to some extent in a thermonuclear bomb explosion, for that matter, you'll quickly form very, very neutron-rich elements. I'm going to see if I can pause this so I can talk to it. No, it's not going to let me pause it. I just have to talk faster. So you form neutron-rich heavy elements. So you go very, very far to the right and very, very far to the top right, and then you decay back to stability. You beta decay back to stability. But you get this sort of characteristic 3-peak abundance structure because there are magic numbers of neutrons that give you increased nuclear stability, sort of similar to the way in chemistry where having certain numbers of electrons in the valence shell of an atom gives you more chemical stability. And so right around those magic neutron numbers, you get pileups of atomic abundances. And this process produces basically the heavy elements on the periodic table. So every element that's highlighted here in yellow is produced by the rapid neutron capture process. And that includes sort of jeweler's elements like gold, silver, and platinum. And so some people in sort of popular press like to call these neutron star mergers bling novae. So this is just a really, really cool sort of parable in the interconnectedness of science, because we need to up until last year we didn't really know where in the universe these heavy elements were produced. For a long time, we thought they were produced in supernovae, but that doesn't quite work. And so neutron star mergers were were another very promising candidate. And there was a, before the binary neutron star merger discovery, I remember one really cool paper in Nature where people had done ocean floor sediment, samples and looked at sort of the geologic history of astrophysical events that disperse our process material. And so you could actually look in the geologic record and find evidence of some astrophysical event that's producing lots of our process material. This is the signal that we recorded on August 17th, 2017, the day after my birthday. Sorry. So this is going to take a while longer to play because this is a binary neutron star merger. So the lighter a system is, the longer it stays in our sensitive band, the slower it evolves through frequency, and the higher the final frequency. So just because, the binary black hole merger merged at about 350 hertz. This one is going to keep on going. And so just the length of this chirp, I'm sorry, I was talking over the part where you would have heard the final whoop, but you can tell from sort of the track that this makes on the time frequency plane what the masses were. So this was the first binary neutron star merger ever detected. We initially detected it in LIGO Hanford, and we could see this chirp track very clearly. The chirp was also visible in Livingston, but there was also a huge glitch in the data. Our detectors are extremely glitchy because of environmental noise sources and also just sort of, instrument issues in various subsystems. And so this glitch was caused by saturation of a photodiode. And this is one of the worst glitches that we've ever seen in data that we've, considered of science quality. We were able to model that glitch and remove it out, and then underneath that we also saw that nice, perfect chirp. That was cool enough, but even better, Advanced Virgo, our European counterpart facility, had just come online in their advanced configuration just weeks beforehand. And so for the first time, we had a network of a globally dispersed network of 3 gravitational wave detectors with astrophysical sensitivity. And that allowed us to do localization very, very accurately with that extra baseline. So these are the localizations of binary black holes that we detected up to then. And this is GW 170817. So these span areas of like 1,000 square degrees on the sky. This is 30 square degrees on the sky. And so if you're trying to hunt for some visible light signal, you'd much rather deal with something like this than with something like this. So everyone was very, very happy about this. And basically every astronomer in the world kicked into high gear for the next month. There was even a coincident short gamma ray burst. So gamma ray bursts are intense flashes of hard electromagnetic radiation. Half of them are known to be associated with the collapse and death of a certain type of massive star, and the other half of them were thought to be caused by these binary neutron star mergers. And there was a coincident detection of a short gamma ray burst by the Fermi and Integral satellites that proved at that moment that at least some short GRBs are associated with binary neutron star mergers. So even better, because the source was so well localized, we could actually we could take sort of many different approaches to finding this counterpart. So we could take a very wide field of view telescope and just tile that whole region, that whole green region there. Or we could pick out individual galaxies and look at each of them with a very small field of view but very sensitive telescope and check if anything new had appeared in that galaxy. Both techniques were taken, and there were sort of 6 teams that almost simultaneously announced the discovery of a bright, rapidly evolving optical transient in our localization region, coincident with a galaxy that was at a distance consistent with what we measured with LIGO. This is that galaxy, NGC 4993. What I'm going to show on the left are images of the transient in optical, and on the right I'm going to show spectra. Just a second, is it playing? Can't tell. Oh, yeah, it was already playing. So the source started off very blue, and it faded and became redder and redder over the course of four days, and then when it peaked and then started to drop off. So this evolved much faster than any known type of supernova. The spectra looked nothing like any other type of transient that we know about, but the behavior of these spectra and sort of these broad bumps agree spectacularly well with the predictions for what a kilonova should look like. And so this is now the observational prototype of a kilonova. I should add that it was also detected in X-rays and radio, and the X-ray and radio emission is extremely important for understanding sort of the bulk properties of the outflow from this event, and understanding the geometry. But the X-ray and radio are a subject of could be the subject of a whole talk or a whole conference for that matter. But you can actually still detect it in X-rays and radio to this day. So I don't want to give the impression that we've sort of solved all the problems in this space with this one event. Far from it. We've done some really impactful things. For one, for the first time, we've determined the host galaxy of a gravitational wave source. We've measured the speed of light. We've measured the speed of gravitational waves and checked that it is in fact the same as the speed of light by looking at the time delay between the gravitational waves and the gamma ray burst. We showed that binary neutron star mergers are indeed the central engines of short GRBs. We've shown that binary neutron star mergers are the dominant site of R-process nucleosynthesis in the universe. And we've constructed the prototype, the observational prototype of a kilonova. But there's a lot more to do. There are a lot of things that we would learn from a merger of a neutron star and a black hole. That's something that that we hope to do in one of the next few observing runs with LIGO. We'd like to sort of understand the phenomenology and understand what determines the features that we see in electromagnetism. We'd like to determine what is the nature of the object that's left over when you collide two neutron stars. Is it another heavy neutron star? Is it a black hole? Is it a neutron star that spins for a while and then collapses? We don't know. We'd like to characterize the properties of the host galaxies of these sources across cosmic time. We'd like to determine what are neutron stars made of? What's the equation state of matter at nuclear densities? And we'd like to measure the Hubble constant, which describes the rate of expansion of the universe using gravitational waves. Okay, so now I'm going to switch gears, and I've sort of covered all the science that I want to talk about, and I want to show you some of the uses of Python in our project. So this is a photograph of the LIGO Hanford control room. I believe that this photograph was from the first acquisition of LOCK. So LOCK means getting the arms of the detectors, getting the laser light to be resonant in each of the arm cavities of the detectors, and then getting the arm cavities in resonance with each other. And those are the steps that you need to go through to get to astrophysical sensitivity. In this picture, this screen that looks sort of bluish that this woman in the black vest is looking at, that is displaying sort of the graphical user interface that we use to control the interferometer. It's called it's something called EPIX, which is an experiment control software package that's developed out of Argonne National Laboratories, and it has a user interface that looks like something out of the early 90s. but it's pretty common in large physics experiments. Now that is what actually talks to the low-level hardware, which consists of a few million filters that are implemented in FPGAs and various modules. But the actual automation of the whole system is done using Guardian, which is sort of a distributed hierarchy of state machine automatons, and it's used to actually lock the detector and automate transitions between different states of operation. So it's built using, so it represents, for each little subsystem, it represents a graph of state transitions using network X. Each little worker is running in a tightly managed sub-process using multiprocessing, and it talks with the hardware through epochs via some Python bindings. So LIGO is controlled by Python. So next, in the control room, so we're running the detector, and now we want to look at the data and see if it looks reasonable. And so for that, we use a tool called GWPI. This is a tool for, or it's a package for accessing data, both public data and internal unpublished data, doing basic signal processing techniques and analysis and plotting. So it's used to do a lot of quick look investigations in the control room, and it's also used to produce our detector summary pages, which are live collections of about 800 different figures of merit that we use to look at the health of all the different subsystems. So the main use is in the control room and also in detector characterization and data quality, as well as science outreach and open data. And as you would expect, it relies heavily on NumPy, SciPy, Matplotlib, and AstroPy. And this is what one screen of those summary pages looks like. Next, Gravity Spy. This is probably more interesting to a lot of the people at this conference. Gravity Spy is a project that combines both citizen science and machine learning to identify and classify glitches in LIGO and Virgo data. So we have sort of a zoo of all different types of glitches. We know what caused some of these glitches and other ones we don't. What we like to do is remove glitches by identifying some auxiliary instrumental channel that can act as a witness to predict when the science data is going to be affected by a certain type of glitch. But that only works for some types of glitches. And so the idea here is that people can go onto Zooniverse and they can volunteer to classify glitches according to different morphologies, and then we use those classifications to train machine learning algorithms, and we hope to deploy those machine learning algorithms online in our next observing run. And this is just a dimensionality reduced representation of this space of glitches in LIGO data created using the TSNE algorithm. So we've run the detectors, we've looked at the data, we've post-processed it, we know it's okay to analyze. What do we do with it next? So next it's going to go out to our computing clusters. We have our science channel, which is H of T, the strain, that we're measuring in each detector. So that's a 64-bit double precision floating point time series sampled at 16 kilohertz. You collect that for a year. It's like 4 terabytes of data, no big deal. You could fit it in, one or two, SSDs in a briefcase. But we also record an additional, say, 5,000 so-called fast channels, which are channels that are associated with auxiliary sensors or control loops and are sampled at 2 kilohertz or above. And then about 200,000 slow channels, which are sampled at sort of 16 hertz to 64 hertz. So depending on what you're doing with the data, you might need just the science channel H of T, or you might also need some of these auxiliary channels. But you're going to do that analysis on one of our tier 1 LIGO data grid clusters. There are 3 tier 1 sites. The biggest one is at Caltech, which consists of 18,000 CPU cores and a bunch of GPUs and some Xeon Phi processors as well. We have clusters at each of the sites, which each consist of about 2,500 cores. And then we have tier 2 sites, which are operated by LIGO Scientific Collaboration member institutions. And the three tier 2 sites are at the Albert Einstein Institute in Hanover, which consists of 42,000 CPU cores and 2,000 GPUs. There's a cluster at UW-Milwaukee, which is about 3,400 cores and also some GPUs. And there's also a cluster at IUCA, which is about the same size as UW-Milwaukee at about 4,000 cores. So what are you going to do with the data on these clusters? Well, we're going to want to compare the data with a bank of model waveforms produced by General Relativity or approximations to General Relativity. And so we're going to do matched filtering. And then we're going to use Markov chain Monte Carlo or nested sampling to determine the properties of signals that we detect using matched filtering. And these sort of compact binary coalescence analyses take up about half of the time on our clusters, and the other half is other types of sources, which I don't even have time to talk about today, but are also really cool. So underneath it all, there's LAL-Suite, which is, among other things, our strategic reserve of forced acronyms. LAL-Suite stands for LSC Algorithm Library. LSD stands for LIGO Scientific Collaboration. If you keep going down the rabbit hole, you'll find that this is a quintuply nested acronym. It consists of a lot of heritage C code that's wrapped with SWIG, plus some newer Python code. Up until about 2011, it was sort of the standard practice that LIGO graduate students and postdocs would deposit code that they wrote as part of their thesis into LAL-Suite. So it consists of some parts that are extremely highly engineered, and then some parts that are sort of a grab bag of different levels of code quality. But some of the software, some of the sub packages of LAL-Suite are extremely important to our analyses. The most important ones are LAL-Frame, which is used to read and write a domain-specific binary data frame format that we use for storing H of T. LAL-Simulation, which consists of a comprehensive library of waveform models. So we have various ways of approximately solving Einstein's equations for a compact binary. One of those ways is with sort of a series expansion called the post-Newtonian approximation. And the other way is sort of by fitting phenomenological waveforms to numerical relativity. Both of these techniques result in really, really dense code. I've put one of the scarier examples here. This is actually one of the simpler waveforms too. This code is really, really difficult to write, really, really difficult to test and cross-validate against other waveform approximants, and so this is something that's going to be with us for a long time. And finally, there's LAL inference, which is Bayesian inference using MCMC and nested sampling. So LAL-Suite used to be a huge challenge for LIGO newcomers to install and use. That's improved a lot recently thanks to Wheels and Mini Linux. So like I said, parts of this are Python, and so now you can just pip install it. And this is something that I worked out how to do along with Alex Nitz. And so I'm posting these to SciPy. So next we have our search pipelines. So one of them is called GST-LAL. So it's a real-time streaming compact binary coalescence detection pipeline. It's written using GStreamer, which is a media processing framework for the GNOME desktop. So you have little signal processing elements that you can plug together into a more complicated pipeline. And so we use this to implement a bank of 650,000 match filters that we convolve with the data in real time. And we use Python to assemble, monitor, and post-process the output of this GStreamer pipeline. Then there's PICBC, which is a framework for studying gravitational waves with a strong emphasis on compact binaries. It does everything from data conditioning to detection to parameter estimation and visualization. It's really, really approachable. It's very easy to install, and there's lots of documentation and tutorials. It supports GPUs through CUDA, and so this is a very, very powerful option and a very easy way to get started as a member of sort of the broader astronomy community. Parameter estimation. After we've detected the sources, we want to determine the masses and spins and the sky location and distance of the source. And so we do that using Markov chain Monte Carlo, nested sampling, and also more domain-specific techniques that are really tuned to the problem that we have to solve. And again, there's LAL inference, which is a part of LAL suite, PICBC inference, which is sort of a next generation, almost pure Python replacement, and also Baystar, which is a code that I wrote as part of my thesis, which focuses on just determining the sky location and distance, and also comes with sort of a suite of tools for working with LIGO probability maps. So we've determined the parameters, and now we need to send an alert to astronomers. So we pool together all of the results from all of our different pipelines using GraceDB, which is sort of our central marshal and clearinghouse. And this is written in Django, as you would expect. And then we need to do sort of follow-up analyses, such as running that rapid sky localization, vetting candidates and deciding which ones are reasonable to send out, and generation of the data products that we want to send to astronomers in low latency. And so this is at this level, you want to you have a task that has to use 64 cores on a single machine for about 10 seconds, and then be ready to accept the next job right away. And so we use Celery for that. So we've sent alerts. Now the data is out there in the public, and now people outside of LIGO need to be able to get access to it, and they do that through the Open Science Center, which is a portal for accessing and analyzing published LIGO data. So there's a data archive and a trove of tutorials and Jupyter notebooks that you can download or run in situ in Binder or on Microsoft Azure Cloud. So some conclusions. Python is integral to every stage of operating LIGO and performing and analyzing gravitational wave observations. Software in our community is tending toward a more modern, a more vibrant, mostly pure Python development model, partly because science outreach is becoming such a very high priority. But we have these sort of legacy packages, these C codes that contain all of our waveforms and so on and so forth, that we have to work with and distribute and package, and so that's a challenge. But the landscape and the options for doing that has significantly improved in the past several years with options like Conda, Mini Linux, Docker, and Singularity. And this is changing how we work with our clusters and also how we interface with the broader community. LIGO is a huge collaboration. It consists of over 60 institutions and almost 1,000 scientists around the world. So what I've had a chance to talk about today necessarily represents just a small slice of everything we do. And so please, talk to me afterward and ask questions. Lastly, we're going to build bigger and better gravitational wave detectors after this, where we'll be able to see out to sort of the edge of the observable universe with the next generation detectors that we want to build. And there's a whole unexplored gravitational wave spectrum, very analogous to the electromagnetic spectrum, that will probe with future facilities and future missions, such as the Laser Interferometer Space Antenna, which is sort of like LIGO in space. With which we'll be able to see mergers of supermassive black holes in other galaxies. So there's a lot to do, and Python has been important for the whole journey and will continue to be so. And with that, I'll just thank you and ask for your questions.
So I think there's a microphone here.
Should we bring up the light?
Yeah, can you bring up the light? So. All right, is this on? Test, test.
Hi, I'm here.
Yes,
Short.
please go ahead.
I'm Julie. Thank you so much. That was an excellent talk. I think it's super exciting that we have observations of the site of the R process. And so my question is, because it's a neutron star binary merger, do you think that this has, wow, that's bright.
Where are you? Oh, hi.
Hello.
No!
Oh, no. Do you think that this has implications for the initial mass function of POP3 stars, since supernovae have been sort of ruled out as the main site for the R process?
Oh, that's a good question. So the question is, what implicate? Could we turn on the lights, please? This is. Can we have a multi-messenger question and answer session? So the question is, what does the R process, as we've learned about it from neutron star binaries, tell us about population 3 stars, which are the oldest stars? That's I don't know the answer to that because, sort of stellar evolution and population synthesis is not my area of expertise. But one of the cool things is that with the next generation of detectors, we'll actually be able to look back far enough that we can see, we can sort of look at, epochs in cosmic history where we expect there to be a lot more population 3 stars. And so we can can maybe look at the distribution of masses as a function of redshift that we're seeing merge, and maybe say something about about stellar evolution as a result of that.
Thank you.
Yeah.
Other questions?
Hi. One of the questions I've seen a few animations of gravitational black hole mergers, and one of the questions in my mind is, does the black hole have any shape other than spherical after it merges, or in an ideal model, does it have a spherical shape right after it merges?
So right after it merges, it's going to be deformed, and it's going to actually ring down and settle down into a spherically symmetric configuration.
So it'll be elliptical for a bit, ellipsoidal, to say? Okay,
Yeah.
Thanks.
Yep.
Hi, I was curious if you could elaborate a little bit on how you guys deal with the floating point calculations of dealing with the really very small numbers that you have to handle.
Yeah, well, so often it's not a problem because one of the first steps in most of our analyses is whitening the data. So our data has a very, very specific, well, our noise has a very, very specific power spectral density, and we need to flatten that out and normalize it before we do match filtering. And so normally when you do that, that also takes care of sort of bringing the data down to a more reasonable, to a very limited dynamic range.
One more here.
Thanks, very interesting talk.
Thank you.
It's good to see how Python is used in such a large scientific collaboration, and it seems like you've gotten happier over the past few years. But if you had one wish from this community, what would it be?
Oh, I think that's tough, but I think that I wish that the skills that you get by interacting with with big, open source Python projects, like how to get a pull request through, or how to interact with code that's written by someone else, or how to package software, how to make it durable, and how to test it, how to do continuous integration. These are things that you learn by going out and submitting a patch to Matplotlib, but they're not things that I mean, a lot of people at least in our community, who are extremely proficient in Python still don't have these skills. And I'd like there to be like a really approachable way to learn those things.
Ties into yesterday, some,
Exactly.
doesn't it? Yeah. All right. Well, I guess I'd like to say in about the most understated way possible, well done.
Thank you.
It's truly a maestro effort of orchestrating a lot of really visionary ideas and cutting edge science, but also a lot of elbow grease to really make that happen. And I'd like to turn to you and say, well done, right? I mean, holy cow. I just kept going through package after package after package on that sheet, or on your slides, and I mean, 70% of them are from this room. So amazingly well done, and thank you so much for a wonderful presentation. Let's thank our
thank you.
speaker.